of Tomasz Limisiewicz, and the topic, of course, is multilingual language models. So the floor is yours.
Yes, thank you for this kind introduction. So probably you all know me. I'm Tomasz Limisiewicz. I would talk on my recent research on multilingual language model, specifically their tokenizers. So this is a part that I did in PhD. I know that this idea for the seminar is to present already the results of PhD. This is actually the parts of work that left out of the scope of what I'm writing dissertation about. So if you come to my defense, hopefully in September, there'll be non-overlapping side of work, maybe a bit overlapping though. So yes, so let's start by talking about the tokenization, or changing slides maybe first. I need to use this. Click in the window. Okay. Okay. Awesome. Okay. So tokenization in NLP. I know there are multiple definitions, and you're definitely familiar with lots of them. And I know this tokenization has a bit different meaning in theory of linguistics, and a bit different meaning into what we did as engineering part of it. So you definitely know there are different types of representations that we can use to train language models. So there are words, there are characters, there are also bytes, so very low level, and there are subword tokens. So nowadays, most of NLP based on subword tokens. So probably you're also familiar with this schema. So this is the algorithm called byte pair encoding. So here we start for the base of the text representation, in this way characters. Then we look into the text and find the pairs of characters that appear frequently in the text, and then we merge it and add it as another unit in our vocabulary. So this we can think that is intermediate step between character level or maybe byte level representation and this word level, as it's usually described as tokenization in linguistics. And also even here we can have different things that we can call tokenization. So this algorithm has multiple components. So first step in NLP with building tokenizer is pre-tokenization. So actually we need to have some iterative decisions. What base do we use? In the example before I showed there are characters as a base, but some people use also bytes. Or there could be some other also segmentations of the basic units. Then many of the algorithms also decide to first divide all the words by space. So that's we never merge two words. We cannot merge space to any other vocabulary unit. So those are all those preceding steps before even working on subword tokenization. The second step is building vocabulary. So here we base on frequency. We build this vocabulary, so it is in BP, it's this merges. So how do we merge those basic units into larger, which then are the parts of our vocabulary we will use in training the model. There are also different algorithms for that. So some of you could know word piece that was first introduced with BERT or Unigram LM. And the last step of tokenization in NLP is segmentation algorithm. So we already have vocabulary, a subword vocabulary, and now we need to have a function how to transform the text into the sequence of tokens. So in WordPiece, for instance, we just transcoded all the text from left to right, but it's not optimal because sometimes in Word we can find longer tokens. So in the newer packages such as sentence piece, we rather focus on finding the longest subword token inside each word. So here I will in this talk mostly mostly focus on vocabulary building. Yeah, I know it's a lot already. So yeah, if you have any question during this talk, like just stop me, because there'll be like lots of different papers which are like similar to each other, but like each of them can have like different question. I'll try to build from simpler things to more complicated ones. So it's like important if you can stop me at any point and just ask questions. There'll be also a few natural places where that's dedicated for questions for specific work. So I will just make a pause here. So maybe let's do like first pause. Do you have like any questions toward tokenization algorithms? I think nothing else. Like okay, I think it's like just everyone is at least a bit familiar. Maybe it was just like to organize the terminological terms to it. So to make things even more complicated, I was working on multilingual subwords. We're not focusing only to English and building those tokenizers into English. And there are new problems that arise when you want to tokenize multiple languages. And as in multilingual settings, the biggest problem is data. So we have data for high resource languages, English, German, French, so those like easily available. But for many languages, it's much harder to get any data or some data. So this unbalance between the resourceful of languages be also manifested in how well can we represent this by tokens, because those methods based on frequency. Unfortunately, just increasing the size of vocabulary, so that's like could be one solution, does not really work well with multilingual setting. So instead of learning actually new subwords valuable for other languages, we could be left of learning some artifacts that we see in high resource languages. So we could, like, for instance, when you look into GPT-3 or GPT-4 tokenizer, there are separate tokens representing one space, other tokens separating for 2 spaces, 3 spaces, 4 spaces, 5 spaces, and like until 20 or something spaces. So like, because like we base it on frequency, those things that are not that interesting for linguistic aspect, but just appear a lot in the data, and usually in those high resource languages, will be very much overrepresented in this subword vocabularies. So the first work I will present is about measuring, so introducing some metrics for multilingual tokenizer and looking into whether we can know by just looking in tokenizer before even training the model, whether this is a good tokenizer that suits well this multilingual settings that we use. So this was previous year work with Fiji Balhar, master students, and my supervisor. And here specifically, we looked into 2 aspects. So one was token overlap, so how much token vocabularies of different languages, if they're comparable across languages. And the second one was token allocation, saying how much of vocabulary is useful for given language. Both of those aspects were already checked before, but usually previous works focused on checking differences between transfer from one language to another. So what is the difference between checking like donor and target language? But we rather wanted to map tokenizers, so say that like this features of tokenizers is better. So like if we've given tokenizer have higher overlap, then we can have higher transfer. So here we kind of marginalize the effect of the choice of the language, of the pair we want to transfer, but rather want to focus on those effects of choosing particular tokenizers. So in this work, we the main components was a comparison of the 4 tokenizers. There were 2 types of unigram tokenizers. So like this is like the method of getting this vocabulary units, and also BP. Then we had some measures which were dedicated for particular tokenizers. So one was vocabulary allocations. When we had like simple metrics or characters per token, for instance. I will talk a bit more about this later. and also for vocabulary overlap, which we measured by divergence. The last step was based on tokenizers. We trained small language models and checked how much those properties of different tokenizers affect the performance of the model on the original pre-training task of language modeling and downstream tasks such as part-of-speech tagging, name entity recognition, natural language inference, and cross-lingual retrieval of sentences. So let's start with very simple metric. In this paper we had two, but like I would just focus on this very simple, but which also had like very high correlations with the performances. So like don't complicate things too much. We just looked how many letters is in each of the subwords. So here we compare two segmentations of the same sentence, and we see that the first segmentations has much larger subwords, like meaning this will be better. This tokenization methods better represents this language because it uses longer tokens. For overlap, it was like a bit more tricky because like we didn't want to just see if the tokens are shared between corpora of languages, but also how frequently they are shared. So we had distributions of tokens in two languages. So for instance, here, French and Vietnamese. And we wanted to compare if like the same tokens are used frequently in given corpora. The natural metric to see, like compared similarity between distributions is divergence. We particularly use Jensen-Shannon divergence because it's symmetric. So we have like the same number of similarity from French to Vietnamese and Vietnamese to French. So this is basically saying whether from corpora of two languages, if we're using the similar tokens like frequently. So now I will present the results, and this is like important to understand this plot. So this is like our canvas when I put all the results from this work. So here we have vocabulary allocation with scale from -1 and 1, and we'll put the points on this canvas depending how strong is correlations between vocabulary allocation and the point which represent given task. And the same is with vocabulary overlap. So first we looked into allocations between these three tokenizers, and we see that definitely BP had something appeared here. That's not part of presentation. Okay. BP has higher allocations, but the first surprising result was we have higher allocation, but we actually are worse in the original task in language modeling. So here we measure the performance in language modeling, and something that was a bit surprising is that like the higher allocations we have for a language, the worse we are in predicting the token. But then we thought about it a bit more, and we thought, yes, we are making it as like pre-training tasks. So now we're predicting much longer tokens for given language. So it's actually harder to predict those tokens because we mask much larger chunk of information. So we saw this negative correlations between allocation and masked language modeling. So it's on the left side of this plot. However, even though those models with the tokenizers that have lower allocations, even though they perform worse in language modeling, they had better performance in downstream tasks. So from name entity to part of speech and dependency labeling. So idea was like our finding here was that yes, the task is harder because we mask larger tokens, but like it helps the model to learn this linguistic information to perform better in those end tasks. We also look into the comparison of overlap of those for those tasks. So here we have compared two types of tokenization. Here we have original method of unigram tokenizer, and lower we have one intervention. We just prevent any overlap between tokens. So the tokenizer is trained the same, but like in one, we just forbid any overlap. And then we see that actually for part of speech tagging, we had slight increase in the results when we didn't overlap the tokens, but it was detrimental to name entity recognition. And the explanation of this is in those syntactic tasks, they have lots of ambiguity when we compare the same chunks. So we have, for instance, a word composed of just letter A, which in Czech could be conjunct, in English is determiner. So like those are something that can be actually helped when we don't share the tokens across different vocabularies of different languages. So this is like how it's maps on our plot. So in name entity we have like positive effect of having higher allocations for all those tasks, and with name entity we have also positive effect of overlap, but for syntactic task we have negative correlation. The last one was sentence level task. So here we have natural language inference, when there was like not much difference between the tokenizers that have different levels of different allocations numbers. But for those tasks, so name NLI and cross-lingual retrieval, it was really important in cross-lingual transfer to actually overlap the tokens. So we here see that forbidding overlap in tokenizer can be very detrimental to the results of cross-lingual transfer. So here is the complete canvas of our results, showing that, yeah, for those sentence level tasks, we have small effect of vocabulary allocations, but overlap is very important for them. So to sum up those findings, we found out that overlap effect varies. So like for some tasks, name entity recognition and sentence level, it's helpful to overlap more tokens. And for syntactic tags, it actually have negative effect. We actually, this is like also inspires, like, so like we are all also working with Kati now, who tries to propose new metrics for checking how those tokens interact between languages, when we hope that we can also have like these correlations across the task. So like it's like a bit yeah, suspicious. Like I mean, like not ideal that we have metric of tokenizer that we cannot really predict whether it's helpful or not for a given task. So let's have this varied performance, which was also criticized by some reviewers who just wanted to say one metric, which would say it is better to overlap more tokens. But yeah, it just how it was more analytical. So it was, we just said like the overlap could be helpful, but not for all tasks. Allocation is basically important, but mostly for the low-level task. And yeah, lastly, we highlight the importance of first checking tokenizer between training language model, because this is like much cheaper and can save lots of computations of training multilingual language models without tokenizer that doesn't represent well all the languages. So I'll do short pause for, yeah, sure.
One question.
Sure.
Slide. So you said it, but I will stress it out that when we see that, let's say, the vocabulary overlap of almost 1 for the sentence retrieval, it doesn't mean that the vocabulary overlap is high, but that the correlation of the vocabulary overlap with the given task,
yes,
for example, sentence retrieval, is high. And I forgot about it, and then I realized maybe. Okay, And the question is, the correlation is computed on how many numbers? You have shown just the three models, but actually I think it's for all the languages.
Yeah, so this is like a bit more like completely statistical thing, because like we have data for 20 languages. So we need to marginalize this effect of language. So we need to match their distribution across different languages. And then we have like 60 numbers for each of the correlations eventually. So we have 3 tokenizers and 3 points for each of those.
So 3 tokenizers, but still times the 20
Yeah,
languages.
yeah. I mean, it depends. Like if
you normalize the per language, but still for each language you have 3 data points for the 3 tokenizers. And the final question is, haven't you looked like whether the correlation somehow differs for different languages even after the normalization, or if it's not driven by something else, just this is like average over different dimensions?
That's like this. Yeah, I feel like it's like statistical consideration, like whether how much similar are those languages. Like, so definitely there are some other effects that we want to marginalize. So like here we want to marginalize the effect of the language, right? So like we want to say that like this is similar behavior independent which pair we take. So that's we have like two factors. Like the similarity between languages is important, but like other than that, because like there were multiple works that already studied that this is important. But here we wanted to rather check how it's important to have like those properties of tokenizers. So yeah, so that's why we marginalize these differences of languages. We also use Spearman correlation, which is less susceptible like to those to this like statistical factor of like, for instance, having like a bit different variance for the languages, because here we just compare ranks.
Yeah, thanks. And last, very small question, the MRR metric for masked language model, what does it mean?
So that's mean reprecausal rank. I always don't know if I pronounce it correctly. But like it's considers like not only if you predict the right words, but if you didn't predict, you get some points for predicting in like second and third position. So I think like first position is 1, the second is half, and then 1/3. So like that's like it's yeah, I think it's usually now like this, or perplexity is now usually used in evaluation. Okay. I go to more results. So yeah, we talked about these allocations across languages. So now we go more into fairness analysis. Now we won't consider really the differences into languages, but more into specific domains inside one language. And here we looked into representations of female and male professionals in the data. So here now we have like also like we compare language, but mostly we have like those two groups that differs in their representation. So not only one language can be underrepresented, but also one group in given language. So usually when you look into professional names across all the languages we analyzed, so it was German, Hebrew, and Spanish, we saw that there are much more entities of male than female professionals. And this also affects how those words are tokenized. So here we have an example for German, the word for lawyer, so Anwältin and Anwalt. And like we see that like one of them appears much less in the data, and therefore will be split into much more tokens. So like 4 in contrary to 1. And this we also observe, so already tell you that like this is like more effect of the data than tokenization. So we did like this, I will show the results. So here we focus on machine translation task, and we translated the sentences from the data set of Stanowski et al., which included the examples that follow Winograd scheme sentences. So for instance, here we have one profession, and a pronoun. So, and here, based on the context, we can say that like this pronoun refers to this professional. So then when we translate it to morphologically rich language, we need to decide which form of this, which inflection of the noun of the doctor we will use. So like in Czech, it will be lékař, lékařka. So this is something that we don't have like that much problem in English, but then in translation, it can lead to lots of problems. So Stanowski et al., they proposed those metrics of checking the accuracy of translating male and female professions into those target languages. And like they were interested into the difference. How much better are we in translating the sentences that contain the male professionals than female professionals? But also they checked there were some annotations which jobs are stereotypically female and male. So they checked how better we are in translating those pro-stereotypical, so stereotypical name of professionals, so like male doctor, and anti-stereotypical ones. And we so like they showed that like all like machine translation systems show this kind of bias that like usually they're better they're better in translating male occurrences than female, and also pro-stereotypical than anti-stereotypical. And we thought that this could be also the result of tokenization, especially in those morphologically rich languages, that like just those male entities will be split into less tokens, making them easier to generate. And for first glance, it's looked so that yes, there is like correlation between this delta S, so like this stereotypicity gap and like number of tokens. Both examples were connected. This is like an example for German, and the same for this gender gap. However, then we looked also into confounding variable, which is like just frequency in training, and found out that when we also consider how often those entities appear in the training data, the influence of tokenization is marginal. So like the problem is actually in the data, and tokenization seems to don't like make the problem worse, at least in this. The helpful thing about tokenization, sometimes we don't have access to the data. So then we can check tokenizer. Those are very strongly correlated, the frequency of the data and like how much how many tokens we are splitting those words. So this could be a hint. But much more important thing is to think about the data, so have balanced data than to have balanced tokenization. So those were main finding that yes, there was correlation between the tokenization, the segmentation levels and the preference on specific gender forms. However, when we take into account how often given gender or like stereotypicity group appears in the data, then it's much it's like not statistically significant. Okay, here I'll have some yeah, again like
what MT models you used in this when measuring the correlation and the dependent and independent variables? And more importantly, was it trained on the same data as the vocabulary? And wouldn't it be the case that sometimes we have them, like the vocabulary is fixed for some reason, maybe we are fine-tuning BERT, but we can influence, or from now another like BART, let's say.
Yeah.
But we can influence, we can like collect more data, let's say for the gender-bias problem where we have more anti-stereotypical roles. And then the question would be, would it then help? And I guess it would somehow help, but maybe still it could be affected.
Yeah, so I didn't talk about all the results. So like let's go one by one. So like the models. So we checked the Opus models from Helsinki. So for those we had data. The second models we tried MBART. So based on and this we couldn't find the like exact data they trained. So, and the whole analysis of this like multifactorial analysis went down just for Opus models, because that's like the only model we could like be sure that we have like the same data the tokenizer was trained. And the second question is that if fine-tuning on more balanced data helps, and yes, it does. And it wasn't our finding like that was done before. We also tried some interventions like doing fine-tuning with updating tokenizer and the ÚFAL, and actually also here, updating tokenizer wasn't that important. So there's just marginal change. So that's why basically our finding here was that like tokenizer is much less important than the data we're training. Thanks. Adam?
Very basic question.
Wait for Mike.
So a very basic question, I think. What exactly did you refer to when talking about this pro and anti-stereotypical?
Oh, yes. Sorry, I didn't explain that too well. So like there are data and we have 40 professions which are basically annotated. This is based on like US Department of Labor. So they have like statistics, how many professionals are of which gender in given profession. So based on this, we have like 40, like it was also not ours. It was like from Stanowski et al. And like they also based on something on some previous work. That like, for instance, doctors are usually male. It's in US. Like in Czech Republic, it's actually 50-50. So it's like very, very similar to US distribution of of professionals in given profession. And yeah, so like there was like just 40 professions. There was nurse or lawyer, and like yeah. So that's like also not perfect. And another thing is that like it's also dependent by the culture. So like this is like very US centric.
So like a construction worker would be very stereotypically male profession.
Yes,
right?
that's an example, for instance, of stereotypically male. Yes. Okay. Okay, so this is like only one thing like that we also studied in gender bias. Now I want to go back to like problem of multilinguality and those biases based on high and low resource languages. This is actually not the results of our work. It's like something that was very interesting phenomena that was also inspirations for another work we were doing. Is yeah, this multilingual bias that I've showed in the previous slide. So like this first work that like it has effect on the performance, but like its ramifications of tokenizations are much more wide than like just having like those like performance changes in the model. So for instance, there is also the question about costs. If you used for instance, ChatGPT API, then you basically pay by each token. And like when you ask the question to a model in different language, then you basically pay depending on which language you chose, because like in different languages, the same content, the sentence with the same information will be split in different numbers of tokens. So for instance, here you have an example of the same question asked in English or in Greek, and the corresponding tokenization and how much it affects the cost of usage software. So this is like also something that is unfair towards speakers on particular languages. Other thing is like when you use few-shot learning, then over-segmentation and like context prevents you to fit enough examples in the context you're allowed to use like in one question. So like then also the same problem. You could like have much more examples for one language, but like for instance in Greek or like some even lower source languages, you'd be able to maybe just include one demonstration less, which is like huge impact on the performance, because like those models often learn from the demonstrations. And here are like some examples across the models. So they might differ a lot, basically, which depending like which model do we choose, and also how do they perform tokenization. But here we have like these examples of those 8 languages. Sometimes they're much closer. Oh, that's like important thing that like for all languages, we checked it on PAL data. So like basically, this is like segmentations of the sentences in each of the languages, but like information content is the same across all languages. So like the bar here, like the higher bar means like just like this sentence is over segmented. Either the content is the same as this sentence. So this is like could be like huge difference, like especially when you consider like low resource languages and languages which doesn't have Latin scripts. So like that's like the main factors that here. So like for instance, here we train Yiddish. We wanted to train some model on Yiddish, and like basically all the models just butcher this language into lots of small tokens. And there's also the like interesting findings that we have. Like this was like work mainly for Jiří Balhar. It's like part of his thesis, but yeah, we unfortunately haven't yet published it. But he was that's like not nice graphics. You need to imagine the flags here. He wanted to check the popular method of balancing the data in different languages. So it's called alpha sampling, and it's used in training of many models. So like those models usually have larger fraction of those low resource languages, and there's a parameter which just decides how much upsample this low resource, how much upsample should we use for upsampling. An actually interesting thing about work that Jiří mostly did is that like that low resource languages can be very impacted by this choice of alpha. So like in tokenization, so we can have much better statistics for them. And high resource languages doesn't worsen that much. So like for tokenization, we can use much stronger upsampling than in training actually. And there's also alternative methods which even like goes beyond upsampling. For instance, cap some languages. So like just like don't use some data for like so sample that strongly that like basically we have the same amount of data for most high and mid resource languages. But then I had like this question: is better sampling enough? And the short answer was no. So what I came to that like that's like won't solve also all of our problems to just upsample some of languages. And this is also dependent like on the thing that I mentioned at the beginning. So what base do we check? So nowadays, most of subword tokenization algorithms use bytes as those base for learning merges and the new tokens. And already this base is very much different based on different on the language. So for instance, we compared the amount of bytes that parallel corpus has in different languages, and like in many cases, it could be more than 2 times longer than like English text. So like the representation only on this level will be biased toward high resource languages, and then ones using Latin script, because they will be on the base will be represented in less bytes, and only then we start merges. So like based on this, you would need to give like tens to hundreds additional merges to those low resource languages to even catch up with the base representation of English. And in reality, because there's also data imbalance, those languages gets even less mergers. So that's like something that even when we have matched corpora, basically in the number of sentences in different languages, basically this base representations prevents us to get like the same level of informativeness of those subwords across languages. And this is actually led to another work that I was doing mostly at University of Washington last fall. So it was new look on byte representation. Like many of you, I know that already heard about it because I already presented it on our seminar in Troja. So yeah, maybe I'll just give you a shorter overview here. So basically, that's the problem I was just describing. That like we have the same sentence in 3 languages, so English, Czech, and Telugu, and they mean basically the same. The information, the content is the same. So roughly at 12, we have the same thing in Czech and in Telugu, but like the number of bytes we need to represent this sentence in English is much shorter than Czech, and like it's especially much shorter than Telugu. So we here say this multiply of like over 2 to represent the same sentence in Telugu. So basically here our motivation is to find like this representation which be one more fair. So like basically we'll represent the sentences of different languages into bytes or this basic representation, which is more comparable across languages. And the second is more efficient, meaning like they will produce like longer, shorter sequences for different languages. So here we introduce this idea called MIND, which we called morphologically is driven byte level representations. So here, instead of using characters as a base of getting the representations of bytes, we use actually morphemes, which number is much more comparable across languages than number of characters. And also the way we construct it is that we treat each language equally in constructing this representation. So therefore, we can get one like mainly the much shorter representations than previously with UTF-8, but more importantly, they're much closer to each other. So this is like this green codes. If I have time, I can give you like more overview how the method works later. So just like that, I would just firstly focus on what we found here. And so here's a comparison between byte segmentation. So here we see this long tail of languages, mostly non-Latin scripts, where in parallel corpus we have much longer sequences for those languages. And then when we compare it with MIND segmentations, we basically drop this tail. So there's like still not exactly equal, but like much closer across different languages. So it's like much better base that we can use for training the model or starting BP from this step. This is comparison of compression. So this comparing like this byte representation and this MIND representation. And it's important that we use the same number of this basic vocabulary. So like as in byte, there's like just 256 units that we represent as a byte. But for many languages, for all the languages, we get shorter sequences, but this compression, so the drop in the sequence length, is most visible into this long tail of low resource non-Latin script languages when we can get over 70% of the compression. For many Latin scripts, we still get some compression, like 10%, 20%, but it's much less. So like it depends how much underrepresented the language more, the poorest gets the most. So like this, like both more shorter, but also more equal. And the last step of this work was to find like how these new representations will affect language modeling. So here we trained a language model based on this new representation. Here we actually don't use subword tokenization at all. This is like the architecture that is based on, like operates directly on byte level. So it's called byte T5. But in our approach, we just change those bytes into those morphologically driven bytes, so MINDs. And we have some hypotheses. So one is that like will be more efficient thanks to shorter sequences. The performance should be more equitable. So like you should have it should be easier to model the sentences of using non-English, and we thought that it could also be better to language modeling, but also downstream tasks. So first observation, was that yes, it was more efficient. So like across levels. So here we compare like how much time we saved in MIT5 compared to BIT5, plotted against like how much we compress the sequence. It's kind of expected that like higher the compression, the more time we save on inference. And this is almost like less visible for those. So red ones are Latin script, and like for other languages, it's a much higher decrease of inference time. Then from the language modeling results, it was even stronger. It was like interesting that we also have like lower, so we use some sort of normalized perplexity to compare different languages, but we also have much lower perplexities for those low resource languages. But even for Latin languages, we have it's easier to predict them, which we thought it could be the result of having like the representation that easier to learn. So basing this on morphology instead of characters, as in UTF-8, it could be helpful already even for the languages that we don't compress the sequences that much. This is like very visible here. So here we compare so here in box plot is represent each language, and the distribution is the perplexities for different, there are 1,000 sentences in each language. So we see that with this MIT representation, we basically are much closer. So those those distributions are much more narrow and are much closer to each other across languages. So we don't have this huge effect of choosing the language, so base representations on the perplexity. So I would say it's like the main finding of it, that like changing this representation, so how do you represent language, can have huge impact on how do we perform in language modeling. Lastly, we also checked downstream tasks. And here it was interesting because it didn't translate that well to downstream. It could be also like on the architecture we chose, because like we had to reformulate the downstream task as a sequence-to-sequence task. So like some tasks were kind of not natural, especially semantic parsing, when we get like worse result that with byte representation. But usually the results were very close, very similar, with the improvement in inference time over the regular bytes, which comes mostly from those compressions. Okay, so that concludes this part. Yeah, so we introduces this new representations called MIT, and like this bridges the segmentation gap between languages, which also has those positive effects on language modeling in byte level. This is already almost the end, so you can like ask questions regarding this work or regarding some other questions. Oh yes, Inji.
Go ahead. I have two questions. One is sort of being a devil's advocate. You said this oversampling worked quite well if you oversampled more aggressively. Isn't the reason that you compensate for the different bit length? So if you like include it, or if you compensate it for the for the different bit length in the oversampling, wouldn't you get a similar result like that compared to mites?
It's okay. So you mean like sample based on not on like the number of sentences, let's say, but like you want to sample based on the size. You want to sample the same.
Yes.
Okay.
Or actually both, like first to have the same number of sentences, so you have like the same information content, and then if something has like 3 times longer byte sequences, then multiplied 3 times.
Yeah, I mean, like, definitely there could be a way to do over something better than it was, but like that means like that you need to very strongly, like you need to be more strong over upsampling of this low resource than anything that have been tried till now. So that's like something that haven't been yet tried. Is like could be interesting thing like that. Maybe we could try on bytes. There could be like also some. I recently saw like some paper. I need to read it. Like on like what that's this optimal number of BP tokens per language. And this could be also not only affected by the data, but also this like features of language. So like some language can have like also like could depend on morphological richness. And unfortunately, BP just focuses on this frequency. And I think it's like on some level, it could be suboptimal. Like for instance, like I didn't say it yet because I cut the technical part from the last paper, use Morfessor. And I think that using Morfessor is much better to finding those informative chunks than using BP because it only doesn't have only the frequency part, like compression. It's like not only this, like the aim of the objective of the algorithm, but it also has this part that like wants to find the subwords that are most shared across different words in lexicon. So that's like something that's very important, like basically more, that's why they're more similar to morphemes than like BP chunks.
Thank you. And my second question, I don't know if it's a good question to discuss here because it assumes that the rest of us also know how the stuff works, which I do from the previous seminar. But what would you do if you wanted to you have this trained might representation and you want to add a language?
Oh yes.
What would you do?
Didn't you ask it last time?
No, I did not.
I thought you did, but like yeah, I have like those additional slides here. So like this is like yeah, I really didn't want to go over it like to mention how it works because we have some time, but like I don't want to torture you with all those steps.
We can talk about it.
Yes, but like
any
basically the thing is that in Might we basically had to free some capacity from UTF representation, and this is like very like very I don't like what's the name, like capable, like capacious, like you have like lots of size by like getting rid of of symbols that is not that often used. So we actually with using might, we didn't use up all of this free capacity for new tokens. So it's like easy to just implement, just add it, like just add new morphemes into something that we have. So like we didn't reach the capacity of languages. We use 100 languages. But like we could still extend more.
Okay, thanks.
Yeah, and like this is also like related. So we also check like even like without adding the language for many languages. So like this is like left byte and might, by sharing some tokens, we could like decrease their sequences. The only difference is this SAL, which I was forgetting what's the language it is. But like the feature of it was like this was used like some very low result script that weren't used by any language. So it's still generalized a bit to languages that haven't been seen in training, in development of this might. But yeah, like I think it's like pretty not surprising that it doesn't generalize to new script that haven't been seen.
Okay.
Yeah. So if you want, I can go over over the technical details, but I know like people interested most in it already were on one talk, so I didn't want to spend too much time on this.
If I may, from the remote participation, Yeah, I would be interested in hearing the details because I missed that part. But you can decide. You're there in the room. So I was just curious, but without knowing the details, it's difficult for me. Do you like merge the same morphemes across languages, or if they use different scripts, they stay totally apart? From the table that you have shown, I understand that you kind of like strip some Unicode early characters or early bytes and use them. So you like compress at the very technical representation of Unicode, and it's not related to the linguistic content of the morphemes. I would say but I don't know. So I was wondering if the sharing is promotable somehow more than what you did. And what came to my mind is speech as well. So if you would be creating not mites for like morphologically inspired units, but some fines like phoneme inspired units.
Okay.
Would that make sense?
So yeah. So maybe again, I would just start with repeating because it's a very concrete question, and then I would like go more into like divagations about the second question. So yes, so we don't share if we've add morpheme just once. We don't have like two places for the same morpheme. There is some decision. So like in Mite, like there's like this decision, like it's also in UTF-8, like basically how many codes, like code points, how many bytes do we devote to this morpheme? And like basically this is decided how much this morpheme is imported for a language. So always the morpheme which has smallest representation will be kept in Mite. So we just like, it's kind of like higher preference by being important in other language, but it'll be only once in this vocabulary. And yeah, I would like go into more detail, so like just offline if it's okay.
Yeah.
Okay.
And the speech.
The speech. So yeah, it's also interesting. Like I was talking. Yeah, also like there's Yulia Tsvetskov, so she's also from UW. She also like we were talking like she was very interested into this, like also like trying to do it on phonemic, like not morpheme but phonemes. I thought that in text it could be a bit hard because I remember when I tried some cognate task when they also operate often in phonemes. And for some language, it was easy to transcribe from text to phonemes, but like for I think most of languages we considered, it was it would be hard to find a method of I think it's called the model to replace it with phoneme. So I think this could be more coverage issue than optimality issue.
Yeah, thank you.
Sure, thanks.
Yeah, I did. So I personally don't have a lot of experience with Morfessor, but I wanted to ask, because the experience I do have shows that it's not ideal in terms of linguistic knowledge.
Yes.
It has these gaps. I don't remember if it over segments or under segments, but it usually does both depending on what you do with it. And do you think that improvements in morphological segmentation could lead to improvements in language modeling?
Yeah, I mean, so like when we look into Morfessor, yeah, I'm like, okay, it's hard truth, but like actually here we cared more about this equality than like if it's like valid morpheme. So like this like can still be like there are definitely some cases when it's definitely not on the like wouldn't be linguistically valid, like the segmentations we get there. So it comes with all the limitations of the Morfessor. And like we also use some hyperparameter which say that like the morpheme vocabularies for each language should be similar, which is not true in theory because like some languages are more like are richer, like have higher morphological richness than others. So by imposing this, we say, okay, don't segment this language that well, but the other, we just care like to have like this equitable segmentation. I think more thing about Morfessor is that like the main like selling point for me was that like it doesn't base only on frequency. So like when I looked into like the loss the Morfessor is optimizing, it has on one side of this frequency, but on the other side has like this loss which saying in how many lexicon lexemes this segment appears. So this is something that like it's not visible in BP on sentence piece, but it's like it's a Morfessor feature. So and this is like something that like can match those representation even though we don't start from the shared base.
I understand. I wouldn't be surprised if, or I wouldn't be surprised if the language model that then operates on these mites wouldn't actually really care about morphological accuracy that much, because any errors could be, it learns to correct them basically internally. I would expect that to happen. But my other question is, did you try taking into account allomorphy at all?
No. This is like not, so like those are not morphemes, those are morphs. So I mean,
I
like
understand, but if I don't know, it was just an idea that you could, for instance, try and assign similar strings, similar morphemes, similar indexes, or something like that. You didn't do any of that.
No.
Okay, thank you.
Okay. That's everything from me. Yeah, maybe just like few words for the closing remarks, summarizing all those works. So yeah, we need to care about tokenization. So I think like now this topics is getting like kind of more traction. I don't know if you also saw like there's like people there's like more work going on, but like I think like maybe on some minimal scales it doesn't help that much if we have like already well represented language, and maybe we add like 100 more tokens to vocabulary, 1,000 more. It wouldn't help, but like it can really be harmful for many languages, especially in over segmentation. So I rather would, like with tokenization, I think it's more interesting to look into those low resource languages and high resource. I think we won't help with tokenization that much there. And yeah, and also think like that still like there's some lesson learned in NLP that we can take from linguistics and morphology, because like we cannot like just treat like just UTF-8, which is basically based on some alternative decisions, like first include English and then other more languages. So this could be not optimal. So we could like propose something better and more like from which we can train better language models across languages. Okay, thanks.
Yeah, thank you. Thank you very much. I've just pointed out that the second question is something where linguists may be of some opinion, and if not help us. Well, I think we had questions during your talk, so now is space for more questions. Are there no questions on the online? No? No, okay. Well, so let me thank you for your presentation. And as I've said, question number 2 is something which I would be interested in if you have some answer to that. So next time we still have that's the PhD session. We still have one more session after that, but we have no session on the 20th, because I feel that many of us, if not most of us, will be on their way to LREC and calling in Italy. So there will not be many people here. So thank you very much and looking forward to see you next time.
Thank you so much for attending.